So let's talk about limits at infinity and horizontal asymptotes. All right, so let's go back to this function, f at x is equal to 1 over x, but let's talk about what this looks like for x very large. Well, for x very large, we see that we're taking a very large number and taking 1 divided by it. So the function values get very small. So indeed, what we can see from here is that this curve, as it keeps going, the values are staying positive, but nonetheless getting very close to 0, and they're hugging really closely this x-axis here. So we sort of want to say, and we will say, that the limit as x goes to infinity of 1 over x is going to be equal to 0. So some functions have limits at infinity, some functions don't. For example, if you take f at x is equal to sine of x, this isn't going to have a limit at infinity for the same sort of oscillatory reason that sine of 1 over x doesn't have a limit at 0. This function just keeps bouncing up and down, and it doesn't really hit a limit. So this is an example of something that doesn't have a limit at infinity. But a lot of functions are going to, and basically what we can do is the same sort of limit laws that worked for finite limits are going to work for limits at infinity too. So taking this as read, let's work through some infinite limits. So let's work through some examples. So first let's do the limit as x goes to infinity of, let's just say, x squared plus x minus 3 all over x squared plus 5x plus 1. So how are we going to work through this? Well, we basically have our same limit laws here, and we just have to turn this into something where the limit on the top and the limit on the bottom both exist. So, of course, if we just plug infinity into the top and bottom, well, we can't really do that, but nonetheless, you could imagine what you'd get. If you plug huge numbers up here, you're going to get huge numbers. Similarly down here, we have to do something to this. But what we can do is the following, is we can divide out the top and bottom by x squared. So why would we do this? Well, notably we can. We can divide by x here, and what will we get? Well, we would get this. Over this. Why this is helpful is because now the limit of the top and the bottom both end up existing. We know that this limit and this limit are going to be 0, and either by the product of limits or composition of limits rule, if you have that 1 over x goes to 0 as x goes to infinity, so are these guys. So now we can use our quotient of limits rule and get the following. Infinity, sorry. But now we can break these apart, but all of these individual pieces have limits. By, and I won't write them all down, but by sum of limits, constant multiple, product, etc., just the same rules we've been using, we can turn this top thing into the limit as x goes to infinity of 1, plus the limit as x goes to infinity of 1 over x, minus 3 times the product of these two guys here, 1 over x and 1 over x, all over similarly on the bottom. But now we can just plug things in, because we know what these limits are. The limit of 1 is going to be 1, and everything else is 0. So this gives us this all over this, which is 1. And we've computed the limit. Let's do a similar example now. with a slightly different trick. Let's say we take the limit as x goes to infinity of x plus 1 all over x cubed plus 5x plus 2. So let's take a gander at this. What is going to happen here? Well, the degree of the top is smaller than the degree of the bottom, so we sort of expect the bottom to grow larger than the top. So you might guess that this should go to 0, because we have a lower degree thing which doesn't grow as fast as a higher degree thing, so we expect this limit to be 0. But how do we show this? Well, we can do the same thing as before. We just have to get a limit upstairs and downstairs, both of which exist. And we can do that by dividing everything in sight by x cubed on the top and bottom. And of course, remember why we can divide by the same thing on the top and bottom is that's just multiplying everything by 1. But here, this turns into, well, we divide by x cubed and we get 1 over x squared plus 1 over x cubed. All over this, 1 plus 5 over x squared plus 2 over x cubed. But now we can again compute all of these limits. By using the product rule over and over again, as we have here, we can see that this limit and this limit and this limit and this limit are all going to be 0. So I won't write out every single one of those steps again, but indeed we can use the quotient of limit law to turn this into the limit of the numerator divided by the limit of the denominator. And as I just said, we can now plug everything in to get upstairs 0 plus 0 and downstairs 1 plus 5 times 0 plus 2 times 0. But it doesn't really matter what's downstairs because we have a 0 upstairs and this limit is going to be 0. So this is how we use the limit laws to compute limits at infinity, very similarly and just as easily as how we use them for finite limits.